In this lecture, we are going to discuss about cold reserve and hot reserve. So, in previous lectures, we have already discussed about different kind of loads and what are the different kind of factors which affect the cost of electricity tariff and uh, different kind of factors which is used when you analyze any kind of power plant and its generation. So, the topic of this lecture is cold reserve and hot reserve. So, this is very interesting topic and which is very important and at the point of view of the power generation process. So, you can see here that the learning objective is to introduce students to the basic theory of power generation process and familiarize students to the principle of operation and hot reserve and cold reserve. After this lecture, I'm expecting from student that student will be able to understand different thing of power generation process and uh, um, would be able to understand what is cold reserve and hot reserve and how it is useful in any kind of power plants. So let's start with the content. So, content of this lecture is introduction, cold reserve, and hot reserve. So, first we have to understand that what is cold reserve. So, it is that reserve. Reserve means what do you understand by reserve? Reserve means that something which is you are reserving for later. You are keeping for later. So, it is that reserve generating capacity which is not in operation but can be made available for service. So, cold reserve means that you are reserving something and it is not in operation. But if you later, if you required any kind of electricity or anything, you can use this capacity or cold reserve for utilization. Hot reserve, this is the it is that reserve generating capacity which is in operation but not in service. Okay, hot reserve means that it is continuous in operation and for later you can't use it. Okay, so it is not in service and it is in operation. So this is your hot reserve and cold reserve. Now let's start with the spinning reserve. So what is a spinning reserve? It is that reserve generating capacity which is connected to the bus and is ready to take the load. So there are three reserving capacity. One is your cold reserve capacity. Second one is your hot reserve capacity, and third one is your spinning reserve capacity. So cold reserve capacity means that you are not that you are not using that reserve capacity at that time, but you are using it later on when you require. And in hot reserve capacity, it is continuous in operation, but this is not in service. And spinning reserve means that it is ready to use. Whenever you want, it is ready to take the load. So there are three type of reserve capacity of a power plant. Now, next is your what is the initial cost of power plant? So actually, each power plant have two costs. One is your operating cost, and another one is your capital cost. So capital cost means when your power plant is constructed, then what are the things which you required, and for those things you have to there are some expenditure which is divided in like this. So one is your initial cost of the plant, which includes. Second is your land cost, because if you are going to settle a plant, then first you have to purchase the land. Second one is your building cost. If you are going to set up a plant, then you have to construct a building over there. So there is a cost which includes building cost. That is your building cost. That is your equipment cost. If you obviously, if you are, you know, uh, constructing a power plant, there must be some equipment which is used when you generate the electricity or transmission or distributing. Next is your installation cost. is the part of your capital cost, and overhead charges. This is also the part of your capital cost. So this is all about your this is all about your different costs. So one is your rate of interest. So what is your rate of interest? Rate of interest is, it is the difference between the money obtained and the money returned, and may be charges as simple interest or compound interest. So this is very important when the tariff calculation is done. So these charges are considered. Next is your depreciation cost. So depreciation cost means that it takes into account the deteriorates of the component over a period of time. So that is your depreciation cost, and this is into account the deterioration of the component over a time. So this is the difference between the money obtained and the money which is used for tariff. So these two points are very important. What is your rate of interest and what is your depreciation? So it takes into account the deteriorates of the components over a period of time. So next is your straight line depreciation. So depreciation can be divided into many parts. One of them is your straight line depreciation. So what is your straight line depreciation? In straight line depreciation, straight line depreciation is the simplest and most often used technique, in which the company estimates the salvage value of the asset at the end of the period during which it will be used to generate revenues, and will expenses a portion of original cost in equal increments over the period. So the salvage value is an estimate of the value of the asset at the time it will be sold or disposed of. It may be zero or even negative. So salvage value is also known as scrap value or residual value. So this is very important. That is your straight line depreciation. So straight line depreciation is very easy and very easy to calculate. There is some formula by which you can easily calculate the straight line depreciation. So if you install a equipment, it is some useful life. After that, it cost start to reducing. It due to its aging effect or something else. So the salvation of an estimate of the value of the asset at that time it will be disposed of. It may be zero or even negative. So salvage is also known as scrap value or residual value. Residual value means after using that equipment, how much cost is it remaining. So this is your depreciation cost, and next is your sinking fund method. So sinking fund technique, this is the second method by which you can easily calculate the depreciation cost. So the sinking fund technique of calculating depreciation sets the depreciation expense as a particular amount of an annuity. The depreciation is calculated so that at the end of the useful life of the annuity, the amount of the annuity equals to the acquisition cost. The sinking fund method calculates more depreciation closer to the end of the useful life of the asset and is not used very often. So next is your declining balance or reducing balance. So this way of calculating, this is the third method. So by which you can also calculate the depreciation cost. So this way of calculating depreciation falls under the accelerated depreciation category. This means that it sets depreciation expenses as higher earlier on, more realistically reflected the current resale value of an asset. So the way that declining balance depreciation is calculated is by taking the net book value from the previous year and multiplying it by a factor which has been divided by the useful life of the asset. So these are three methods which is very important to understand what is your depreciation. So one is your say, straight line method, sinking fund method, and next is your declining or reducing balance method. Next is your activity depreciation. So this way of calculating depreciation bases the depreciation expense on the activity of an asset like a machine. Multiplying the rate by the actual activity level of the asset will give depreciation expense for the year. So this is all about your depreciation, and these are different methods by which you can calculate the depreciation cost. Next point is your cost. What is your cost of fuel, labor cost, cost of maintenance and repairs? So these comes into the category of your operating cost. When you settle a plant, already we have discussed that there are different type of cost. Yeah, this is. So this is your capital cost when you are installing a power plant or you are constructing a power plant. You are going to set up a power plant. And rest cost comes into the category of operating cost. So this is your depreciation. This is your you know uh, operating cost and capital cost. So we are going to discuss about the operating cost. So this is your operating cost, which fuel cost, labor cost, cost of maintenance, and cost of stores and supervision, taxes. These comes into the category of your operating cost when a power plant is running. Then these are the costs which must be considered. So after calculating operating cost and capital cost, you can easily decide the tariff or the charges which must be paid due to for the electricity. Good morning, everyone. Today's topic is numerical problems, which is based on your basics of power generation system or power generation process. So, we have already studied about different power plants like nuclear power plant, gas power plant, thermal power plant, and hydropower plants. So in this lecture, we will discuss about some numerical problems which is based on those plants. So let's start with learning objective and outcome. So in this lecture, the motive or objective of this lecture that the student should know about the numerical problems or analysis of different power plants and how the energy efficiency calculation is done for thermal, hydro, and gas power plants. So in this lecture, we will discuss about some numerical problems, and I'm expecting from student after this lecture that student will be able to analysis some numerical problems of different power plants like nuclear power plant, gas power plant, and hydropower plants. So let's start with this example that the question is actually this example is based on your thermal power plant in which we use coal as a fuel, and by burning the coal we convert water into steam, and that steam is thrown onto the turbine, and the turbine rotates, and we convert our mechanical energy into electrical energy. So what is mechanical energy? What is so let's come to the example that in this example we will find out the efficiency of power plant and the power lost. So mechanical energy is supplied to a DC generator at the rate of 4200 joule per second. The generator delivers 32.2 ampere at 120 volt. So the mechanical energy which is supplied to a DC generator is your 4200 joule per second, and the generator is generating that is 120 volt voltage and current which is your 32.2 amperes. So what is the percentage efficiency of the generator? First you have to find out that what is the percentage efficiency of the generator and how much energy is lost per minute of operation. So input power is your which is given to the generator is 4200 joule per second. This is your energy, and you can convert this energy into watt by multiply uh, by time. So you will get that the input power which is fed into the generator is 4200 watt. Now this much of power you are delivering or the generator is getting, okay, and you are supplying this much of energy to the generator. Now we have to find out that after supplying this much of energy, how much power is generated and what power you will get in your output. So you can see that after after delivering or supplied this much of power, you are getting this much of ampere currents and 120 volt. So your input power is your 400 to 4200 watt, and is your output power is voltage into current. So you are getting 120 into 32.2 amperes, which is equal to 3864 watt. So efficiency is P naught upon Pi into 100. Okay. So the efficiency of this generator is your 92%, and the power lost, which is PL is equal to Pi minus P naught. So the loss of power is your input power minus output power. So 336 watt power is your losing, and energy lost per minute of operation. So you can get the energy by multiplying this power into time. So you are getting 336 into 60 is equal to 20,160 joule. So we can see that the efficiency is always less than 1. In other words, every system is less than 100% efficient. Another example is a steam power station spent rupees 30 lakhs per annum for coal used in the station. So coal has a calorific value of 5000 kilocalorie per kilogram and cost rupees 300 per ton. If the station has thermal efficiency of 33% and electrical efficiency of 90%, find the average load on the station. So you can see that the steam power station is spending 30 lakh per annum for coal used in the station, and the coal has the calorific value of 5000 kilocalorie per kilogram, and it has the cost of 300 per ton. If the station has thermal efficiency of 33% and electrical efficiency of 90%, find the average load on the station. So first you have to find out the overall efficiency. So the overall efficiency is, because the thermal efficiency is given 33% and electrical efficiency is your 90%. So you have to multiply these two, you will get the overall efficiency. So 0.33 into 0.9, which is equal to 0.297. Now the coal is used per annum is equal to 30 into 10 to the power 5 upon 300, which is equal to 10 to the power 4 tons, is equal to 10 to the power 7 kilogram. So heat of combustion is equal to coal used per annum into calorific value, which is equal to 10 to the power 7 into 5000, which is 5 into 10 to the power 10 kilocalorie. Now, the second thing, heat output. So overall efficiency into heat of combustion. So overall efficiency is 0.297 into heat of combustion, which is 5 into 10 to the power 10 kilocalorie. So you will get that the heat output of this coal is equal to 1485 into 10 to the power 7 kilocalories. Now units generated per annum, which can be calculated because the unit is always considered in kilowatt hour. So this is the heat of combustion and this is your heat output because the efficiency of power plant is your 0.97 and the which is heat of combustion is your 5 into 10 to the power 10 kilocalories. So the output of your this coal is your 1485 into 10 to the power 7 kilocalories. So unit generated per annum is equal to 1485 into 10 to the power 7 divided by 860 kilowatt hour. So the average load on station is equal to units generated per annum upon hours in a year. So it is equal to 1971 kilowatt. Now let's come to the next example, which is based on your hydropower plant. So hydropower plant is water for a hydroelectric station is obtained from a reservoir with a head of 100 meters and so this is your hydropower plant and the head height of hydropower plant is your 100 meters. Now calculate the electrical energy generated per hour per cubic meter of water if the hydraulic efficiency be 0.86 and electrical efficiency is 0.92. So the water head height is 100 meter and the discharge in hydropower plant is 1 meter cube per second, which is given, and overall efficiency is your hydraulic efficiency is 0.86 and electrical efficiency 0.92. So by multiplying these two, you can get the overall efficiency. And you know the formula which I have already discussed in our previous lecture, which was based on your hydroelectric power plant. So the water available per second is equal to charge rate into 1000 into 9.81, which is equal to 9810 Newton. Now power produced, the formula for power production is equal to W into H into neta, which is equal to 9810 into 100 into 0.79 watt. So the power produced is equal to 775 kilowatt and energy generated per hour is equal to 775 kilowatt hour. So by using this formula, you can easily calculate the power which is producing and the energy generated per hour is your 775 kilowatt hour. Now next numerical is the weekly discharge of a typical hydroelectric plant is as under and the day is your Sunday. The discharge meter cube per second is equal to 500 On Monday, the discharge is your 520 meter cube per second. On Tuesday, discharge your 850 meter cube per second. Wednesday, 800 meter cube per second. Thursday, 875 meter cube per second. Friday, 900 meter cube per second. And Saturday, 546 meter cube per second. So the power plant has an effective head of 15 meter and an overall efficiency of 85% if the plant operates on 40% load factor. So the average daily discharge, pondage required, and installed capacity of proposed plant. The plant has an effective head of 15 meter and an overall efficiency of 85% if the plant operates on 40% load factor. So estimate the average daily discharge and pondage requirement and installed capacity of proposed plant. So first we have to calculate the average daily discharge, and load factor is given, overall efficiency is given, and the effective head height is also given. So you can see that first you have to draw the graph between discharge rate and the days. So you can see from this graph that on Sunday, the discharge rate is your 500 meter cube per second. On Monday, this is 520 meter cube per second. On Tuesday, this is your 850 meter cube per second. On Wednesday, this is 800 meter cube per second. Thursday, it is 875 meter cube per second. On Friday, this is 900 meter cube per second. And Saturday, it is 546 meter cube per second. So the average daily discharge is equal to 500 plus 520 plus 850 plus 800 plus 875 plus 900 plus 546 is divided by 7. So you are getting average daily discharge, which is 713 meter cube per second. Now, so we can see that it is clear from the graph that on 3 days, Sunday, Monday, and Saturday, the discharge is less than the average discharge. Sunday, Monday, and Saturday, you can see from the graph that the discharge is less than, uh, you know, uh, these 3 days, your average discharge. So average discharge is your 713. This is your average discharge. In these 3 days, the discharge is less than your average discharge. So it is clear that from the graph that on 3 days, Sunday, Monday, and Saturday, the discharge is less than the average discharge. So volume of water actually available on these 3 days. So volume of water actually available for these 3 days. So 500 plus 520 plus 546, and in a day we have 24 hours. So meter cube. Uh, so you can convert this hour into seconds. So you will get that this much of no pondage requirement. So we are calculating actually pondage requirement. We have already calculated the average daily discharge. Now you are calculating pondage requirement. So volume, first you have to calculate the volume of water actually available on these 3 days. So this is the water which is available on these 3 days, which is in your meter cube, and volume of water required on these 3 days, because average water which is required is this. So the water required for 3 days into 713 into 24 into 3600 meter cube, which is equal to 2139 into 24 into 300 600 meter cube. So the pondage requirement is you have to minus the actual availability and the requirement. So the pondage required this much of water more. Okay. Now, next uh, problem is that you have to find out the installed capacity of proposed plant. Okay, so the water available is this is your average discharge rate into 1000 into 9.81 Newton. So you can calculate the average power produced, which is equal to W into H into beta overall. So you will get 713 into 1000 into 9.81 into 15 into 0.85 watt. So you will get, you know, 89,180 into 10 to the power 3 watt. So you will get this much of average power. Okay. And installed capacity of the plant is equal to output power upon load factor, which is equal to 9,180 upon load factor, which is given. This is 40% is your load factor, so this is divided by 0.4. Now you will get the installed capacity is 223 into 10 to the power 3 kilowatt, which is 223 megawatt. So the installed, if you're proposing that plant, the installed capacity of this plant will be 223 megawatt. Now, our next example is a diesel power station has fuel consumption of 0.28 kilogram per kilowatt hour. The calorific value of fuel being 10,000 kilocalorie per kilogram. So determine the overall efficiency and efficiency of the engine if alternator efficiency is 95%. So the diesel power station has fuel consumption of 0.28 kilogram per kilowatt hour. Okay. So heat produced by this much of oil is, and the calorific value is given your 10,000 kilocalorie per gram. So to calculate the energy of the heat, to find out the heat produced by this much of oil, you have to multiply the calorific value by the fuel consumption. So you have to multiply 10,000 kilocalorie per gram into 0.28 kilogram per kilowatt hour. So you are getting heat produced by this much of kilogram oil is equal to 2,800 kilocalorie. So heat equivalent of 1 kilowatt hour is equal to 860 kilocalorie, and overall efficiency is equal to electrical output in heat units divided by heat of combustion. So you are getting the overall efficiency of the power plant is electrical output in heat units divided by heat of combustion. Okay, so 860 divided by 2800, which is equal to 0.307, 30.7%, and the engine efficiency is equal to overall efficiency upon alternator efficiency, which is equal to 30.7 divided by 0.95, 32.3%. Let's come to the next example, in which this is based on your nuclear power plant. So as a fuel, we use uranium in nuclear power plant. Okay, so the question is that what is the power output of a uranium reactor if it takes 30 days to use up 2 kilogram of fuel? And given the energy released per fission is 200 mega electrovolt and Avogadro's number is 6.023 into 10 to the power 26 per kilomole. The number of atoms in 2 kilogram fuel is equal to 2 upon 235. Okay, this is its atomic number. So you have to take this much of fuel divided by 235, and you have to multiply by this number. and you will get the number of atoms in 2 kilogram fuel, which is equal to 5.12 10 to the power 24. So these atoms are used in fission, and these atoms are releasing this much of amount energy, which is your 200 mega electrovolt. So these atoms fission in 30 days. Therefore, the fission rate is equal to 5.12 into 10 to the power 24 divided by 30 into 24 into 60 into 60, which is equal to 1.975 into 10 to the power 80. So the this much of amount of energy you are getting per second. Now energy released per fission is 200 mega electrovolt. So 200 into 10 to the power 6 into 1.6 into 10 to the power minus 19, which is equal to 3.2 into 10 to the power minus 11 joule. So energy released per second, that is power output P is equal to 3.2 into 10 to the power minus 11 into 1.975 into 10 to the power 18 watt. So you are getting power output P is equal to 63.2 into 10 to the power 6, which is equal to 63.2 megawatt. So next numerical is that a generating station has a connected load of 43 megawatt and a maximum demand of 20 megawatt, and the units generated being 61.5 into 10 to the power 6 per annum. Calculate the demand factor and load factor. So the formula for demand factor is equal to maximum demand upon connected load, which is equal to 20 upon 43. So 20 is your maximum demand, which is given, divided by connected load. You will get to the demand factor, which is equal to 0.465. Now average demand, which is equal to units generated per annum divided by hours in a year. So units generated per annum is equal to 61.5 into 10 to the power 6, which is divided by 8760 is equal to 7020 kilowatt, and the load factor is equal to average demand upon maximum demand, which is 7020 divided by 20 into 10 to the power 3, and you are getting load factor, which is equal to 0.351 or 35.1%. Next numerical is a 100 megawatt power station delivers for 2 hours, 550 megawatt for 6 hours, and is shut down for the rest of each day. It is also shut down for maintenance for 45 days of each year. Calculate its annual load factor. So you can see that the energy which is supplying for 2 hours is your 100 megawatt and 50 megawatt for 6 hours. So total working hours is your 8 hours. Okay, and so total amount of energy which is delivering in a day, which is equal to 100 into 2 plus 50 into 6, which is equal to 500 megawatt hour, and the station operates for 365 minus 45 is equal to 320 days in a year. So energy supplied per year is equal to 500 into 320, 1,60,000 megawatt hour, and annual load factor is equal to megawatt hour supplied per annum divided by maximum demand in megawatt into working hours into 100. So you will get the annual load factor, which is equal to 20.8%. So this is all about your some numericals, which is based on your power plants like a thermal power plant, hydropower plants, and nuclear power plants. So by these problems, you can easily understand the basic problem. How can we solve the basic problem of nuclear power plant? Okay. Now these are some basic concept of voltage, like the voltage up to 33 kilovolt transmission is calculated as high voltage. Extra high voltage, which is your 66 kilovolt and 132 kilovolt and 220 kilovolt. And the modern extra high voltage, which is your 400 kilovolt, and ultra high voltage, which is 765 kilovolt and above. So HVDC transmission is preferred if the voltage are beyond 500 kilovolt and the transmission distance is above 500 kilometer due to stability problem. So transmission system has voltage levels up to 33 kilovolt, three phase and three wire, no intermediate consumers, feeder and constant current density, which is denoted by J is equal to I upon A, current upon area. Now let's come to the distribution system. So in distribution system, the voltage level in primary distribution is 33 kilovolt uh, to 11 kilovolt. Okay, three phase, three wire system required for this. Now this 11 kilovolt is stepped down by using transformer. So 11 kilovolt is converted into 415 volt, 220 volt, three phase, four wire system. Next is your intermediate consumers. Okay, and next is your distributors and variable current density and size of conductor depends upon the voltage drop. So therefore the choice of proper transmission voltage is depends on economics. Generally the primary transmission is carried at 66 kilovolt, 132 kV, 220 kilovolt or 400 kV. So primary transmission, the electric power at 132 kilovolt is transmitted by three-phase, three-wire overhead system to the outskirts of the city. So second transmission is at the receiving station, the voltage is reduced to 33 kV by step down transformer. Then from this station, electric power is transmitted 33 kV by three-phase, three-wire overhead system to various substations located at the strategic point in the city. So what is your primary distribution? The secondary transmission line terminates at the substation where voltage is reduced from 33 kV to 11 kV. So three-phase, three-wire system. The 11 kV lines run along the important roadsides of the city. So it may be noted that big consumers are generally supplied power at 11 kV for further handling with their own substations. Secondary distribution. So the electric power from primary distribution line is delivered to distribution substation. So these substations are located near the consumer's location and step down the voltage up to 400 volt. So for this we require three phase and four wire for secondary distribution and the voltage between any two phase is 400 volt and between any phase the neutral is 230 volt. Residential lightning load is connected between any one phase and neutral, whereas three phase 400 volt motor load is connected across three phase lines directly. It may be worthwhile to mention here that secondary distribution system consists of feeders, distributors, and service mains. So by this diagram, you can see that this is your distribution system, which is connected to your feeder, service line, and distributor. Feeder is connected to your service main, and this is your distributors. Now we can compare DC and AC transmission system. So first we will consider what are the advantages of DC transmission system. In DC transmission system, that it requires only two conductors as compared to three for AC transmission. There is no inductance, capacitance, phase displacement, and surge problem in DC transmission. Due to the absence of inductance, the voltage drop in a DC transmission line is less than the AC line for the same load and sending the voltage. For this reason, a DC transmission line has better voltage regulation. Next, there is no skin effect in a DC system, therefore, entire cross section of the line conductor is utilized. For the same working voltage, the potential stress on the insulation is less in case of DC system than that in AC system. Therefore, a DC line requires less insulation. So for the same working voltage, the potential stress on the insulation is less in case of DC system that in AC system. So therefore, a DC line requires less insulation. Now, a DC line has less corona loss and reduced interference with communication circuits. The high voltage DC transmission is free from the dielectric losses, particularly in the case of cables. So in the DC transmission, there are no stability problems and synchronizing difficulties. Disadvantage is electric power cannot be generated at high DC voltage due to commutation problems, and the DC voltage cannot be stepped up for transmission of power at high voltages, and the DC switches and circuit breakers have their own limitations. What are the advantages? Power can be generated at high voltages, and the maintenance of AC substation is easy and cheaper. The AC voltage can be stepped up or stepped down by transformer with ease and efficiency. So this permit to transmit power at high voltages and distribute it at safe voltage. An AC line disadvantage is that an AC line requires more copper than a DC line. The construction of AC transmission line is more complicated than a DC transmission line. Due to skin effect in the AC system, the effective resistance of the line is increased, and an AC line has capacitance. Therefore, there is a continuous loss of power due to charging current even when the line is open. What are the advantages of high transmission voltage? Reduces volume of conductor material. So total volume of conductor material which is required for high transmission line is 3p square rho L square upon W B square cos square phi. So it increases transmission efficiency. Transmission efficiency is equal to 1 minus root 3 J rho upon B cos phi approximate, and decreases percentage line drop is J rho L upon B into 100. Limitations of high transmission voltage: the increased cost of insulating the conductors, the increased cost of transformer switchgear and other terminal apparatus. For the same power, same material and same length, if the operating voltage is increased by n times, then the area of the cross section of the conductor is A square is equal to 1 upon n A1. So the power is equal to Vi cos phi, and V2 is equal to and V1 and I2 is equal to I1 upon n. So by this formula you can calculate the power. So there are some numerical which is based on this lecture. So the efficiency of a nuclear power plant in comparison to a conventional thermal power plant is less. Isotopes of same elements have same chemical properties but different atomic numbers. So these are some numericals by which which is based on this lecture, and solving these problems you can you can more understand the concept of these power plants. So these are the MCQs of this lecture.